Hello, everyone. First of all, I would like to thank SFI for giving me the opportunity to share with you our progress on the Operando XPS. This is very challenging topic for XPS, and our today presentation is to show you how we made the progress from post-mortem analysis to Operando XPS to study the lithium electrolyte interface. And the challenge here that we would like to emphasize is what is the reactivity between ionic liquid-based electrolyte and lithium electrode metal. And the idea is to find out the correlation between chemical properties and of the bulk of the electrolyte and the interface between lithium metal and such electrolyte system. And XPS is the well-known technique that can provide very valuable information about the redox process and the solid electrolyte interface properties. So there is the main protocol is used from the literature review is the post-mortem analysis. I will show later what does mean. And our idea is like to go further to a new protocol using Operando XPS. The battery, lithium-ion battery system is a very simple system, but in the meantime, very versatile and complex. Simple because is just a combination between low potential electrode materials and high potential electrode materials, and between we put an electrolyte. So the complexity is due to the versatility of the anode on the cathode materials that we can make, and every redox couple evolve different electrolyte combination. And the main idea is how to find a stable material for high density storage battery, especially with the emergence of electrical vehicle, the battery for electrical vehicle. And for that, we need a stable electrolyte, a safe electrochemical system, and a cheaper batteries. And the lithium metal, as you can see here, is one of the materials that can provide the highest capacity. However, it has several problems. One of the problems is the low Coulombic efficiency, and the main problem, which is has a safety issue, is the dendrite growth. And how can we overcome to the dendrite growth? One of the issue is surface engineering or electrolyte design. And as we can see here, that's the solid electrolyte interface that was proposed by Pellet in 1983, which is based on the mosaic SEI-based system. And the idea here from this work that I will show you, how can we build a new model using a combination of XPS and impedance spectroscopy. So the outline of my presentation is as follows. The first, we're gonna show you the chemical structure of imidazolium-based electrolyte that we have chosen here for this purpose. And we will show you how we could, using XPS and impedance spectroscopy, give a new way to interpret the XPS spectra. The second point is related to the lithium reactivity toward ionic liquid at the open circuit voltage conditions. And the third point that we will emphasize is the lithium reactivity toward ionic liquid in dynamic conditions. This slide, I will show you how what is the difference between and the challenges between post-mortem analysis and operando analysis. In the post-mortem analysis, in the general manner, we cycle the battery in the coin cell or like a prismatic cell, wherever the cell we have, and we stop the cell at different cutoff voltage. Here, for example, is the graphite-based electrolyte. The graphite-based electrode. cycled at different cutoff voltage. So we open the cell in the glove box and we transfer the electrode material to the XPS using the transfer vessel. This is the transfer vessel made by PHI, and which is really has give very practical transfer vessel. So here we can see that we have to study the full cycle. We have to cycle 1, 2, 3, 4, at least 6 cycles, six batteries. So there is like material consuming. And the other approach is to how to we build the operando in quasi-real electrochemical environment. Here we have to design 2 things. The first is to design sample holder that can give realistic electrochemical behavior of the cell, and that's what we will show you how we progress on this work. So in this presentation, we will make like a comparison between a step-by-step study at different cuts of potential in controlled environment and the realistic electrochemical response using Operando XPS. So this is the schema of what we would like to emphasize. So how can we have both information, chemical information from XPS and electrochemical information for impedance spectroscopy. So this is the electrolyte we have chosen to study, is based of imidazolium-based electrolyte, ionic liquid. As you know, the ionic liquid is a combination between a cation and anion groups. And the cation we have chosen is based on imidazolium, which is C1C6 imidazolium here, and 2 anions, TOF-SI and FSI. The salts we have used is RiTFSI. This is the different combination we have used, and for more detail we can have, I invite you to look for our work, our paper. So the XPS, I will show you how XPS is a powerful technique to probe such kind of electrolyte. I would just like to open up, just to point out something, why we have chosen the ionic liquid electrolyte, because it has low vapor pressure. So we can handle ionic liquid in ultra high vacuum condition without problem. So by analyzing the carbon 1s peak, we can see that we have 2 groups of C1C6 in FSI. We have 2 peaks. One is related to the alkyl group, and the second peak is related to the heterostructure groups. Obviously, we can fit this peak using 3 components. However, we have chosen only 1 component for simplicity. We can also, by zooming on this area, we can see 2 features, which is related to shake-up peak, which assigns to the delocalized electron in the imidazolium ring, and which can be related to the pi-pi interaction in this ring. After adding the salt, we can see a new peak, which is related to CF3 group. And when we add C1 group in the methyl group here, in this, by substituting the hydrogen by methyl group, we can see a new peak appearing here. So we can see from here this data that XPS is very powerful to probe the whole chemical structure of our ionic liquid. We present here the nitrogen groups here, nitrogen core level peak. We can see 2 peaks. 1 peak is assigned to the anion groups in TOF-SI or FSI, and the second peak is assigned to the 2 nitrogen in the imidazolium groups. And we can see that we have 2 peak, and the intensity of the anion and the cation is about 1/2, which is representing to the 1 nitrogen in the anion group and 2 nitrogen in the cation group. We found out that the binding energy difference between the cation and the anion is closely related to the nature of the ionic liquid we have used. For example, we have the binding energy shift evolve in this way. And using the hard-soft acido-base theory, we can find that the charge delocalization is closely related to the size of the anion. More the anion is smaller, more the interaction between the hydrogen group in the imidazolium group and the anion is stronger. So this was our first interpretation from this data. So we have also studied the ionic conductivity using the impedance spectroscopy by plotting the conductivity versus the temperature. We can find that the ionic conductivity of the different ionic liquid-based system evolve in this way. So by fitting this ionic conductivity using Vogel-Fulcher-Taman formula, which is B is the critical volume that evolve during the charge moving. That means what is the real volume that move in our electrolyte. And the T0 is the ideal glass transition temperature. So we found out that when we add salt to the C1C6 TFSI group, the B parameters, which is related to the volume that move in our system, increase. While when we add the salt to FSI group, it stays stable. So from the XPS and the impedance spectroscopy, we found out that when we add salt to C1C6 TFSI group, we form a cluster of lithium and TFSI, and this cluster can be the volume that move in our system. However, when we add LiTFSI to the FSI group, it seems that FSI and the C1C6 remained as spectator, and only the group Li plus TFSI minus move in the electrolyte. So I invite you, if you want more detail, to look for our paper published this year regarding this issue. Here we have performed the ex situ lithium reactivity toward ionic liquid at the open circuit voltage. So first of all, we have made a coin cell based on symmetrical lithium electrolyte lithium system, and we record the Nyquist plot during time, the aging during time. And we can see that we have two kinds of information that we can extract. The first one is the electrolyte resistance at a high frequency and the interface resistance at a lower frequency. So we can see that for C1C6 TFSI, the interface resistance keep increasing, and in the same time for C1C6 FSI. In all cases, we have an increase of interface resistance. By plotting the electrolyte resistance change upon a time, we can see that in the case of C1C6 TFSI, the electrolyte resistance keep increasing. Once we add a salt, we stabilize our system. The same conclusion was made for C1C6 FSI. Wherever we add salt to the system, we stabilize the system. So, we have found that there is a differences between TFSI-based electrolytes and FSI-based electrolytes. So we recorded XPS at different after cell aging. Here I report two peaks, the nitrogen core level peaks and the fluorine one, of pure electrolyte, bulk electrolyte, and the surface of lithium after 10 days. We can see, for example, for C1C6 TFSI, that after 10 days, the cation groups is decreased, and after adding the salt, we can see that we stabilize the cation group, which is really matched with the impedance spectroscopy measurement. As I remind you that before adding salt, we have a degradation of the electrolyte of C1C6 TFSI, which can be correlated to this result. And in the case of FSI, which shows by impedance spectroscopy less degradation, we can see that the cationic group is less evolved during the process compared to TFSI-like. So At the surface of lithium, we can see that we have new peaks appears, which is related to the degradation byproduct of electrolyte degradation. So from this result, and from the F1S peak, we can see the presence of lithium fluoride at the surface of the lithium metal. So from this result, we can see that we have formed lithium fluoride, lithium nitride, and polyoxysulfide. And the main conclusion that without salt, the cation is severe. We have seen a severe degradation of the cation, which can induce further anion decomposition. So based on this result, and using some reaction mechanism proposed by Professor Auerbach and Professor Schmidt, we proposed different degradation mechanism of ionic liquid in contact with lithium metal during aging at the OCV for different electrolyte systems. So this was our post-mortem framework. Now let's move to the Operando XPS. How we built the Operando XPS? First of all, we are thanks to the ULVAC 5 4-contact sample holder, which can allow connection between the potentiostat, like the potentiometer, which is here, to the stage inside the VersaProbe 2 spectrometers. So we have built several cell for our Operando analysis. The first cell we call it first generation cell based on which can allow like 3-contact electrochemical analysis. And the second cell, which is based on, we call it second generation, based on planar like electrochemical cell with a cavity which we can put electrolytes inside and 2 lithium electrodes. Here a picture of our cell. And thanks to the secondary electron induced X-ray image, we can, and 10 micrometer lateral resolution, we can point out our X-ray beam at different position at the lithium metal, at the interface between lithium metal and the electrolyte, and inside the electrolyte. So as we have shown before, so we can analyze the bulk electrolyte and the interface between lithium and the metal and the electrolyte. So here are the comparison of our first Operando lithium reactivity toward ionic liquid at the OCV. I report here the impedance spectra recorded in coin cell and the impedance spectra recorded in our Operando cell inside the XPS. We can see that we have a nice shape Nyquist plot and with very characteristic frequencies, similar or closely similar to what we have performed in the coin cell. I would just like to point out that our impedance spectra is not a perfect half circle. It's like we can fit with at least 2 half circles. This is due to the geometry of our Operando cell. So we have plotted, as we have shown before, the electrolyte resistance of both system, coin cell and Operando cell. And we can see a good matching of the electrolyte resistance and the interface resistance of the both system, which give very interesting results regarding the correlation between electrochemical behavior in coin cell system and in our Operando system. Afterward, we have performed a chronoamperemetric evolution. That means we apply the voltage and we follow the current evolution. And in the meantime, we recorded the XPS spectra during these voltage sequences. Well, you can see for 1 volt, we have a decrease of the current, which means we have formed some SEI at the interface of the lithium, at the interface between lithium and the electrolyte. And after that, the voltage stabilized. So the main things we have seen here, that's the peak level, core level peak, shift by the same value of the applied potential. And this shift, we can see that the carbon, nitrogen, and sulfur peak shift to 2 volt to lower binding energy. And once we decrease the voltage, the peak will go back to the original position. So this result is very interesting in terms which can link the surface potential change upon cell polarization, and which can link to the surface Fermi level evolution. Sorry, I will drink some water. So here afterward, we have performed Operando XPS on the symmetrical cell, lithium C1C6 interface, interface, and lithium. We polarized our cell to 150 microamps per centimeter square, and we can follow the voltage evolution. And the red area here is corresponds to the moment where we record the impedance spectra. So we can follow in the meantime the impedance spectra, the voltage evolution, and the XPS evolution in the main cell. So what we can see, first of all, a peak shift, which is related to the polarization of our surface. And we have seen that's the evolution of some core level peak. The nitrogen, we can see here the cation the intensity of the nitrogen from the cation decrease, while we have the formation of lithium nitride. So we can imagine that some reaction mechanism of the formation of lithium nitride. We can see as well the formation of polyoxysulfide during the polarization and lithium fluoride. So in the meantime, we can see that the interface resistance increase. That means we have formed some solid electrolyte. What can be here seen from the stars dot, where we report the interface resistance evolution, where we can see here some evolution which is follow the polarization. And I would like to point out that the pressure inside the XPS start to degrade. We have seen some degradation of the pressure. That means our electrolytes, during the degradation process, we have gas evolution. So we have stopped our experiment here for some safety. So this is our main conclusion. I will just remind you: pressure degradation due to ionic decomposition, interface resistance increase during polarization, and the formation of lithium fluoride, polyoxysulfide, and lithium nitride. So as a conclusion, the Operando XPS may pave the way to study the surface reactivity of lithium to ionic liquid. Here we have shown how we build up the step-by-step our Operando experiment by combining post-mortem analysis and Operando, and we could succeed for a realistic electrochemical behavior of the system inside the ultra-high vacuum chamber. This can open the way for new perspective to study material reactivity in solid electrolyte-based and ionic liquid structure under polarization. So I would like to thank you for your attention, and I hope to see you next time in real life.